reaction mechanisms. So for chemical reactions, it's very, very common that your reaction, the one that you're looking at, is the overall reaction. So that reaction is not showing you like all the steps that needs to happen for you to go from your initial reactants all the way to the products. If you want to know what is happening for you to go all the way to the reaction that you're actually looking at in the book or in the notebook, you need to know the reaction mechanism. So most reactions, they don't happen in just one step. There are several steps that are happening before you can actually get the final products. You're going to form intermediates, and I'm going to show you what those are. And many things will happen from the beginning all the way to the end, or whenever you have your products, final products for the reaction. So the mechanism is just showing you like all the steps that are happening before you get your final products. So I have here like a simple representation of a mechanism. You have two different steps, and from those two different steps you can actually get the overall reaction from those steps. The steps that you're given that are actually showing you the reaction mechanism are called elementary steps. So we can combine those steps to find out a lot of information. Like we can add these two. And when I mean adding, it's literally adding them. Now, you have the first step here and you're forming that compound. And as you can see, you have exactly the same thing on your second step. So you're forming that compound in your step 1, but then you're using that one in your step 2. So at the end, you're not going to have any of that compound left because it's been formed, but it's been used up in the second step. So that is going to cancel out. Anything that it's the same, exactly the same thing with the same physical state and everything, and it's in opposite sides of the equation, you can cancel out. And that substance that you're canceling out, it's an actual intermediate. It's not going to be part of your overall reaction, but you're actually getting that intermediate as part of the mechanism. Sometimes it's very hard to identify an intermediate experimentally. Okay? So that's the first thing that you're going to be doing, checking if you have any intermediates, and you can cancel them out because they're not going to be shown in the final equation. Then I'm going to check what I have left. I cannot cancel anything else. So I have here that one from step 1. This one, I'm not writing it down because it's an intermediate. Then I have an O, and I have 1 mole in my step 1, and I'm getting an additional mole of NO in step 2, which means that you're going to have a total of 2 moles of that reactant. And then you're moving towards the product side. You don't have any products from step 1 because that's an intermediate, so you're just getting the product that you have in step 2. Okay? So whenever you're given the elementary steps, right, which is showing you the actual mechanism for the reaction, you can get the overall reaction by canceling out any intermediates. Now, we can describe like any elementary step by looking at the molecularity, which is just telling you how many particles you have reacting in each step. So when you're determining the molecularity, you're actually looking at one specific step. You're not determining like the molecularity for the 2 steps combined or 3 steps combined. Okay? It's for each individual step. So if you have one number of particles, just one reactant, 1 mole of one reactant, you will have a unimolecular step. If you have 2 moles of reactant or 1 mole of 2 different reactants, you will add up those 2, and that will give you a bimolecular. And then anything that has 3 particles or 3 moles of reactant will give you a termolecular. So looking at the steps that I have here, I'm going to determine the molecularity for step 1. In step 1, you have 1 mole of Br2 and 1 mole of NO. So 1 and 1, that's a total of 2 moles, which is the number of reactant particles. So step 1 is going to be bimolecular, and we can do the same thing with step 2. So step 2, no, this is an intermediate, but it's part of your step 2. Okay? So even though you're canceling out your intermediate to get your overall reaction, that intermediate is part of that reaction 2, or that step 2. Which means that that particle is participating in that step 2, even though it's not part of the overall reaction. So this is 1 mole of this reactant and 1 mole of the second reactant, which is going to give you a total of 2 moles, which is two reactant particles. So that's 2. And that one will also be bimolecular, which is the most common molecularity. And one last thing. So when you're determining the rate law, the order for each reactant, you need to find out that experimentally. You're doing different experiments, changing the concentration of your reactants, determining the rate, and then from there you can actually find out if you have a 0 first or second order. There are some cases where you can actually approximate that value using the balanced chemical equation. So I'm listing here two options, but we focus more on the second one. If you have one reaction where you don't have different steps to get your final products, which means that you have only one step in your mechanism, you can actually use that single equation to find out or to approximate the order for each reactant. And you can approximate the order for each reactant by looking at the coefficients in your equation. Same thing can be done when you have a mechanism, but using a mechanism where the rate determining step is identified. If you have several steps in a mechanism and they are labeled, and you have one of them labeled as the rate determining step or the slow step, that one is the one that you can use to approximate the order of your reactant. Now, the rate determining step is the slowest step in your mechanism, and it's going to determine the overall rate of your reaction, or how fast that reaction is going to happen. So in other words, if you have step 1 and step 2, if your step 1 takes 1 hour, right, and your step 2 takes 2 hours, you cannot get your final products in less than 2 hours, because at least you need 2 hours for that second step to happen before you can get the final products. Right? So that's why the slowest step is your rate determining step. Right? So it will take for you to get the final products of your reaction at least the same amount as the amount of time that is taking you to get the slowest step, or a more, okay, or a higher amount of time. Now, when you have a mechanism, and this is what's going to happen, you're going to have your steps, they're going to be labeled. So you don't have to come up with which one is the slowest one or which one is the rate determining step. The actual mechanism is going to tell you, okay, here I have 3 steps in my mechanism, and out of my 3 steps, the second one is the slow one. If that one is labeled as slow, it means that that one is the rate determining step. Okay? So your final reaction is not going to happen faster than what you have for step 2. So using that slow step, we can actually predict the order for your reactants, and looking at the coefficients in your chemical equation. So here I have for you to determine three things: overall reaction, intermediates, molecularity for step 2, and then we're going to find out also the rate law for this mechanism because you have the slow step identified. So I'm going to do my overall reaction right here because I don't want to copy everything again. So to get the overall reaction, you're looking at your steps, you're finding what you can cancel out, and whatever you can cancel out is listed as an intermediate. So while you're doing your overall reaction, you're also doing the intermediates. So let me find different colors so we can keep track of what I'm doing. So I have here NH3, they are on the same side. I have OCl -1 on the reactant. I don't have that one anywhere on the product side. NH2Cl, I have this one here as a product, and I have that one here as a reactant. It's in opposite sides, which means that that one is going to cancel out. So that's one intermediate. Then moving to this one, I have OH -1 here as a product, and I have that one here as a reactant. So it's in opposite sides again. Means that that one is going to cancel out, and it's also an intermediate. And what else I did? Oh, this one already. Okay, this one right here. And 2H5 + 1. This is a product here in step 2, and you're using that one in step 3 as a reactant. So that one, it's also an intermediate. We already know Cl, you don't have that one here, and none of this. So done. We have 3 intermediates, and they're not going to be part of your overall reaction. So I'm going to write down the intermediates here. And you can write down the overall reaction. Now that you know your intermediates, so this is NH3 and NH3, 1 mole in each step. That will give you 2 moles of NH3. And that's done. And then here you have 3 intermediates that are not going to be part of this one, and you have 3 products, Cl -1 from step 2, and then these 2 products here from step 3. So that's your overall reaction, okay? And to get this one, you actually need to identify your intermediate. So we have to do both at the same time. Now molecularity, and I'm asking only for step 2, which is your rate determining step. So the molecularity for step 2, remember, even though this is an intermediate, the intermediate is not going to show in the overall equation, but it's part of your step 2. For you to get these 2 products here, you need this one and NH3, which means that you have to count that one as part of your molecularity because it's a particle that is actually reacting. So you have 1 mole of that one, 1 mole of this one, so that gives you 2 moles, which is 2 particles. And for 2 reacting particles, you have bimolecular. Now the last one, it's predicting the rate law from your mechanism. And we can do this here because of what you have in number 2. So there are only two times where you can actually use a reaction to get the order for your reactants. So this is one of those cases because you're given the mechanism, and in your mechanism you have the slow step identified. So you can actually write down the rate law using the coefficients. It's an approximation. Okay? Most of the time it is correct, okay? But you still have to check experimentally if that's actually what's happening. So rate law in general, right, is going to show you your rate constant, concentration of your reactants, and remember that intermediate, it's participating in your equation, in your actual reaction. So you need to write it down. So rate based on your reactants, right? Rate law, it's telling you like how the rate of a reaction is affected by the concentration of your reactants. So those two are my reactants in step 2, and that's my rate determining step. Now you can predict the exponent for each concentration using the coefficients that you have. For that reactant you have just 1, and for NH3 you have 1. So you can approximate that these orders here for your 2 reactants are going to be 1. Okay? But you can do that only when you're given this slow step in a mechanism.